In this lecture, we are going to begin going over the minimum spanning tree. And before we start talking about a minimum spanning tree, we just need to get an understanding of what a spanning tree is and what the rules are for it. So we have three rules. The first one is we need to be connected. The second one is no cycles. And the third one is the number of edges is equal to vertices minus 1. So number of vertices minus 1. So we'll start with something simple, and we'll say that we have 0, 1, 2, and 3. And we're going from 0 to 1, 1 to 2, 2 to 3, 0 to 3, and 3 to 1. So we see that we're definitely connected. We're able to get to every node from any node through some form of a path or another. But we see that rule number 2 is currently being broken here. So this is currently not a spanning tree, because we see that 0, 3, 1 is cyclic. We can go 0, 1, 3 cyclic, and I mean we can make a couple of cycles out of this. But we also see that we have more edges than we do nodes. So too many edges in this case as well. So for us to make this a spanning tree, we can do 0 to 3 to 2 to 1. That's a spanning tree. We can do 0 to 1 to 2 to 3. That is a spanning tree. And we can also do 0 to 3 to 1 to 2. And that is also a spanning tree. And we can continue making more spanning trees out of this, but I just wanted to show you some examples of what a spanning tree looks like. So these are all spanning trees. So if we want to start looking at a minimum spanning tree, then the sum of weights, the sum of the edges, weights should be minimum. Alright, so if we take our same example from above of 0, 1, 2, and 3, and now we start assigning some weights to them. So we have 0 to 3 is 2, 3 to 2 is 1, 0 to 2 is 3, 1 to 2 is 4, and 0 to 1 is 5. So if we want to create a minimum spanning tree to this, then we want to satisfy our three rules above of it being connected with no cycles, and the number of edges is equal to the number of vertices minus 1. So for us to do this, we can start out at vertex 0, and we see that from vertex 0 we can go to 3 or to 1, but we see that we have an edge of weight 2. So let's take that. And then from 3 we only have one path that we can go, which is 1, so we can go to number 2, vertex 2, and we see that we can go from 2 to 0 or 2 to 1. But if we take 2 to 0, then we create a cycle. Therefore, there would no longer be a spanning tree. So our only path that we can take here is going to be to 1 as well. And now we have a connected graph, and we are minimum because we have 2 plus 4 plus 1 is equal to 7. And every other path that we take from here to create a minimum spanning tree will be greater than 7. So that was a pretty simple example that we could look at. And so now we can create a slightly more complex graph where we can say 0, 1, 2, 3, 4, and 5. And we can have 1, 2, 7, 2, 1, 3, 6, 4, and from 4 to 2 we will go 3, and from 1 to 3 we will go 5. So we'll start at vertex 0 again, and we see that we can go two different directions. We can go to either vertex 5 or 1, and we'll go with vertex 5 because it has a weight of 1. From 5 we can go to 4, or we can go to 1, and again we'll choose 4 because we have the lower weight on that edge. From 4 we can go to 3, or we can go to 2, and if we go to 3 we have 7 as our weight, and if we go to 2 we have 3 as our weight. So we'll go to 2 since we have a weight of 3. From 2 we can go to 1, or we can go to 3. So we will go to 1, and from 2 we can also go to 3 where we have a weight of 2. So here the weight of our minimum spanning tree is going to be equal to 9. And we see that we are connected entirely. We have no cycles, and we have 1, 2, 3, 4, 5 edges, and we have 1, 2, 3, 4, 5, 6 vertices. So this would be our minimum spanning tree. So in the next lecture we will go over the implementation for a minimum spanning tree. So if you have any questions about a minimum spanning tree, please feel free to ask me in the Q&A section. In this lecture, we are going to go over implementing in the minimum spanning tree algorithm. The first thing I want y'all to do is go into your cargo.toml file and import in the disjoint sets dependency. I created a new library section using cargo new taclib section 27 for this section, and then inside of that cargo.toml file is where I have put in the disjoint sets dependencies. So a disjoint set is a data structure that keeps track of a set of elements partitioned into a number of disjoint subsets. So what we're going to use this for is we're going to use union find, which comes a part of this disjoint sets dependency. And this union find algorithm is going to check whether an undirected graph contains a cycle or not. Now, if you remember from the previous lecture, that is one of the rules when computing a minimum spanning tree. We cannot have any cycles in our final tree. So this is going to help us prevent having those cycles. So now that we have disjoint sets in our cargo.toml file, we can bring it into scope by saying use disjoint sets, and we want to bring in union find into our scope. So now we're going to create a couple of custom types to help us as we implement in our MST. So we will say type node equals of type usize, and type weight is also going to be usize as well. And now we're going to create a struct called edge, where we're going to have our destination, which is going to be our node, and we're going to have our weight, and that is going to be of type weight. And now we're going to have our custom graph type, which is going to be a vector containing a vector of type edges. And now that we have all of our custom types set up, we can begin implementing in a function where we can get the edges sorted by their weight. So we can call this function edges by weight, and we're going to pass in our graph, and we're going to return a vector that's going to contain a tuple of our node, and our weight. And then here we will add an edges vector, and we will say for source dest in graph.iter.enumerate, so iterate through the entire graph and enumerate it. And then for edge in dest, we want to push in our edges, so edges dot push source dest edge dot dest, and then edge dot weight. And then just to get rid of all these squiggly so it's easier to see, we know that we're going to return our edges here, so let's go ahead and bring those. So since we're wanting to get our edges by weight, and we now have all of our edges inside of our vector, we can just sort them by key. So we'll say edges sort by key. We'll use a closure here, pass in our tuple by reference, and we don't care about the two vertices or our two nodes. We only care about the weight. So we want to sort by our weight, and that's all we have to do to sort our edges by their weight. So what you can see here is the sort by key is an adaptive iterated merge sort inspired by TimSort. It is designed to be very fast in cases where the slice is nearly sorted or consists of two or more sorted sequences. So we can see that we're just using a iterative merge sort by using our sort by key that comes with our vectors available methods. So now we can create our minimum spanning tree function, and we know that we need to pass in a graph, so we're going to pass in our graph by reference. And to get back our actual minimum spanning tree, we're going to return a vector of two nodes, and we need to put these in parentheses so that we get our tuple back. So we'll create our result vector. That is going to be what is returned to us. So to make sure that we don't have a bunch of red squigglies, we will go ahead and return our result to keep everything happy. And now we will say let mute, and we will call this union find, and this is going to be equal to union find new graph dot length. So again, if you remember, the union find algorithm is going to be used to check whether an undirected graph, which is what we are going to use, contains a cycle or not. So that is what we're doing here with union find. We are checking to make sure that we are not using a graph that is going to contain a cycle. So we can say for source dest, we don't care about the weight in this case, in edges by weight of our graph. So now that we have all of our edges sorted by their weight, which we are getting by calling this, we can say if not union find dot equiv. So it determines whether two elements are in the same set. So we're going to see if source and dest are in the same set. And if they're not, then we want to union find union, and that is going to join the sets of the two given elements. So and then it's going to return whether anything changed. So if the sets were different, we return true, otherwise return false. So we will unionize the two sets from source and dest, and then we will push this result onto our vector. So we will say source and dest. And it looks like it's, oh, we need to make it mutable. There we go. Alright, so that's all we have to do, because our union find algorithm that we brought in is doing a big chunk of the work for us by just making sure that we don't have that cycle in our graph, and then we're getting all the edges by their weight here. So now we're able to check to see if the set that we're trying to unionize is already in our tree, and if it is, then that would mean that we have a cycle, so we don't want to do that. So now we can test this out by saying config test mod test use super and test fn test minimum spanning tree. And so what I want to do is use the graph from our previous lecture. So just so that we have a refresher on it, this is the graph that we're going to use right here. So we're going to create that for our test case. So we will say let graph is equal to vec. This is going to be, not graph 0, node 0. So we have vec edge dest 1 weight 3 edge dest 3 weight 6, and lastly for the node 0 we have edge dest 5 weight 2. Alright, now we have our next vec, so our next node that we're entering in, and this is node 1. And then just for the sake of time, I already typed this out. I just wanted you to kind of see how it's working, so I will just go ahead and paste in the rest. That way you're not getting bored watching me type all this in. And let's see who is not happy here. Closing delimiter. Let me just copy the entire. There we go. That should be happier now. What did I not close? Let's see what we got. Missing structure fields dest. Oh. DEST. There we go. It looks like we have one more. Get rid of that guy. Alright, so now we're good. We have our graph set up. So again, what we have is our graph that we created here in the previous lecture, and we hooked it up right here. So if we see node 0, we go from 0 to destination 1, so node 1 with a weight of 3, node 0 to 3 with a weight of 6, and node 0 to 5 with a weight of, I need to fix that. That is a weight of 1. Let's bring it back up. Alright, now we have node 1 going from 1 to 3 with a weight of 5, node 1 to 5 with a weight of 4, and 1 to 2 with a weight of 1. That is correct. Node 2 to 3 with a weight of 2, and 2 to 4 with the weight of 3. Node 3 goes to 4 with the weight of 7, and node 4 goes to 5 with the weight of 2. So you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges here as well. So our graph looks like it is properly set up, and so now we can test this out. We could say assert equals, and what we want to pass in here is our vec that we want to compare it to. So we will have in here 1 to 2, 0 to 5, 2 to 3, 4 to 5, and 0 to 1. And we want to compare this to MST and graph. So now if we run cargo test, we see that we have A failed here, and we said that we were going 1 to 2, 0 to 5, so I have these two backwards. And if we look at our graph here, 0 to 5, that is correct. 1 to 2, that is correct. 2 to 3, that is correct. 4 to 5, that is correct. And 0 to 1. So I just had these two in reversed order. So let me fix that real quick. And then we will do this by hand just to verify that this is correct. Clear cargo test. So now our test is passed. So if we look at our output of, and we will draw this very smallly so that we can see everything. So we have 0, 1, 2, 3, 4, and 5. We're going from 0 to 5, 1, 1 to 2, that is 1, 2 to 3, 2, 4 to 5, that is also 2, and 0 to 1, and that is 3. So as you can tell, what we have here in our vector, it is returning our values with the least amount of weighted edges first. So that's why we went 0 to 1, or 0 to 5, 1 to 2, because these have edges of weight 1, 2 to 3, 4 to 5, and then lastly 0 to 1 is weight 3. So we have a 1, 2, 3, 4, 5, 6, 7, 8, 9 weights. Well, we see that we have a slightly different output than what we did in the previous lecture, where we went from 2 to 4 instead of 0 to 1. But if you look, the output is the same. So we had two minimum spanning trees that we could have used from here, and our union find algorithm just went with 0 to 1 because it appears that these nodes came first in the tree, meaning that the nodes values were compared. So we have 0 to 1, and those were less than 2 to 4. So it just arbitrarily picked 0 to 1. But what we're able to see is that our minimum spanning tree did in fact work, and we were successfully able to create a minimum spanning tree with a weight of 9, which is what we concluded our minimum spanning tree should have in the previous lecture. So if you have any questions about this lecture, please feel free to ask me in the Q&A section, and I will see you in the next lecture when we start talking about Prim's algorithm. In this lecture, we are going to begin discussing Prim's algorithm. In the last lecture, we went over an implementation for Kruskal's algorithm for a minimum spanning tree. And Prim's is very similar to Kruskal's. It's going to help us find a minimum spanning tree. And Prim's is going to start at a single node, and then it's going to move through the several adjacent nodes in order to explore all of the connected edges along the way. And that's the general premise to how Prim's works. So what we can do is we can create ourselves a little graph, and we'll say we have node 0, node 1, 2, 3, and 4. And now we can draw all of our edges, and let's provide them weights. So we have 3, 4, 1, 6, 3, 5, and 2. So what we can do is we can say our minimum spanning tree visited, or vertex, excuse me, parent node, and then the weight. So we know that we're starting out at, we're going to start out at vertex 0. So this will be our start. We don't have a parent and there's no weight, given that this is our starting vertex. So from vertex 0, we will look at all of the neighbors of vertex 0, and we see that we have 1 and 2. 2 has a weight of 4, and 1 has a weight of 3. So for vertex 1, we will say the parent is 0 and the weight is 3. So we can have our visited section over here, and we have currently visited 0 and 1. From 1, our neighbors are 4 and 2, and we see that 2 has a weight of 1. So for vertex 2, we say the parent is 1 and the weight is 1. And then we have vertex 3 and 4. So from vertex 2, and let's add it in here, from vertex 2, we can get to 0, 1, 4, and 3. Well, we already know that we have visited 1 and 0, so we don't have to worry about those. So all we have to worry about now is 4 and 3. And we see 3 has a weight of 5 and 4 has a weight of 3. So the parent to vertex 4 will be 2 and the weight will be 3. And now at 4, we see that we can get to 1, 2, and 3, but we have already visited 1 and 2. So the last vertex for us to go to is 3, so we can just go ahead and assume our parent is 4 and our weight is 2. And now we have a minimum spanning tree that looks something like this. So we go from 0 to 1, down to 2, to 4, and down to 3. And this is what our minimum spanning tree looks like in the solution. So now, in the next lecture, we will begin implementing in Prim's algorithm, and then we will use this graph as our test case to ensure that this is the output that we are able to deduce during our test. So, I'll see you in the next lecture when we begin implementing in Prim's algorithm. In this lecture, we are going to begin implementing in Prim's algorithm. We are still in section 27, and I just went ahead and commented out all the code from the previous implementation of the minimum spanning tree. That way it's just out of the way, and we know that there's not going to be any conflicting code. So to begin this implementation, we need to bring a couple of items into scope. The first one is reverse, which I will explain when we get to there, and the next one is going to be our B tree map and our binary heap collections. So a lot of this should look really familiar to you because we have implemented most of this before already. So I'm just going to quickly go through setting it up. That way we don't waste too much time going over it. So we get our graph. Now we need to add in creating our edge, and our vertex is going to again implement ord and copy, as well as our edge, ord and copy. And here we're going to pass in our graph that we want to add the edge to. It's going to be a mutable graph with our vertex and our edge generics. We have vertex 1, which is of type V, our vertex 2, and then we have our weight, which is our edge. And since this is an undirected graph, what we're going to do is go from vertex 1 to vertex 2 and from vertex 2 to vertex 1. So we want to call or and insert with, and we're going to have a B tree map new, which calls insert, which calls value 2 with weight. And we can copy and paste this and again reverse from vertex 1 to vertex 2. So our add edge function looks good now. So now we can add in our prim implementation, where we're going to have our vertex implementing an ord and copy, as well as our edge. And we're going to pass in a graph, which is going to be a reference to a graph. And we need our starting vertex. And so that we have something to compare against, we are going to return a graph. That way we have a graph to test against. So now we're going to create a new mutable variable called MST, which is going to be a new graph. And we want to return our minimum spanning tree, so we can go ahead and do that. And we want to keep track of who we have visited. So we will say binary heap new. And now we want to insert into our minimum spanning tree our starting value and put in a new B tree map. Alright, so now that we have inserted in our starting vertex into our minimum spanning tree, we now need to get all of our neighbors. So we can say for vertex with weight in our graph start, we want to push these into visited. And we're going to push them in reverse order, which I will explain why in a second. Alright, so we push in and we need to pass this in by reference. There we go. So if we look at the binary heap, we see that it says this is going to be a max heap. What reverse is going to allow us to do is it's going to allow us to take this max heap implementation and turn it into a minimum heap. And this is important because it will allow us to put all of our edges with a minimum weight first into our minimum heap. And if you remember from the previous lecture, that'll be beneficial because we want to add all the minimum edges into our minimum spanning tree first. So what we can do now, and this will help tie it all together, is while we say let sum, and then we need to reverse it, while let sum weight, and we'll say VT and prev equals visited.pop, and this is where it matters that we turned it into a minimum heap. That way when we pop, off of our minimum heap, we are getting the vertex with the edge of the minimum weight, because that's what we want to check to see if it's already in the minimum spanning tree. So if it is, we can say we need to check if it's in the minimum spanning tree. So if that vertex is in the minimum spanning tree, then continue. That way we can get to the next value that we want to pop off. That way we're continuously trying to make sure that we have the minimum edge being added into our minimum spanning tree, because if it was not already in our minimum spanning tree, well, now we're going to add it into our minimum spanning tree by saying add in our previous, connect it to our vertex, and pass in the weight. And once we add it in, well, now we need to get all the neighbors for that new vertex. So we can say for vertex weight in a reference to our graph and our vertex that we are now at, if the minimum spanning tree does not contain the key of a neighboring vertex, then we want to say visited.push, and again reverse, that way we know that it's being added in properly, of that weight, that vertex that our neighbor is at, and then our parent vertex. And that's all we have to do. So we are successfully looking at all the adjacent neighbors, getting their minimum edges, and then adding them into the minimum spanning tree, moving to that new edge that we just added into the minimum spanning tree, getting all of their edges, and performing the same logic. So our implementation looks pretty sound, so we can now test this out. And we will say config test, mod test, use super, and now we can create our test of testing our Prim's algorithm. fn test prims. So what we need to do is create our graph. So we will say let moot graph equals bTreeMap new. And now we know that we need to add some edges, so we will say add an edge to our mutable graph. Start at vertex 0, go to 1, and our weight of 3. So we are going to create the graph that we did in the previous lecture. So we know we have 7 edges, 3, 4, 5, 6, 7. We go from 0 to 1 with the weight of 3. We go from 0 to 2 with a weight of 4. We go from 1 to 2 with a weight of 1. We go from 1 to 4 with a weight of 6. We go from 2 to 4 with a weight of 3. We go from 2 to 3 with a weight of 5. And we go from 3 to 4 with a weight of 2. So that graph is set up successfully, and now we need to create an answer graph to compare our return value to. So we will create another new bTreeMap. We know we have 4 edges here. We need to change the name of this. Change the name of this graph to ants. And we know that we go from 0 to 1 with 3. We go from 1 to 2 with a weight of 1. We go from 2 to 4 with a weight of 3. And we go from 4 to 3 with a weight of 2. 4 to 3 with a weight of 2. And now we need to assert equals that our prim and graph with a starting vertex of 0 is equal to our answer graph here. And again, this graph is what we did in the previous lecture, and this was the solution we also found in the previous lecture. So we can run cargo test, and we see that our test runs successfully. So we know that our Prim's algorithm is successfully running. So I hope you enjoyed this lecture on Prim's algorithms implementation. If you have any questions about anything that we did, or on anything regarding Prim's algorithm or any other minimum spanning tree that we did in this section, please feel free to ask me in the Q&A section.